Thank you very much indeed. So this is going to be this is a paper or an effort that we did at the University of Tennessee at Chattanooga here in Tennessee in collaboration with TVA, Tennessee Valley Authority, and this relates to the securing what we call off-site power, making sure that the preferred power supply is secure, and that's part of the job. Usually this is a job of the grid operators. They have to relay that information to the nuclear power operators, but it can happen, and I'm going to show, I think I need to advance the slide. So it can happen that during certain weather events, inclement weather, when there's storm, when there's problems, sometimes the visibility is lost, state estimator is not working, and the grid operators do not have that information. And sometimes, and this actually stems from real events that happen to TVA. So they know that this is a possibility, it can happen. And during that time, they're responsible for securing supply to the critical loads, the accident loads of the nuclear power generator, and they have to make sure that this power is secure. And so they know should they keep on using off-site power? Should they switch to local power? Should they switch to start their diesels? They need some information with that in that respect. And so this is what this is all about. And we are trying to provide some guidance to the operators of the nuclear power plant to be able to estimate the strength of the grid and make that determination. Is the grid strong enough to provide this off-site power or not? It starts from very simple theory. So you'll know if you have a radial, if you have a Thevenin equivalent of the power system and you have a load. So if you divide the voltage of the load by the current of the load, then of course it gives you the impedance of the load. By the way, if you divide the derivative of the voltage by the current, then it does not give you the impedance of the load. It actually gives you the Thevenin impedance. It gives you the upstream impedance. So what you're trying to do is to divide the voltage difference by current difference. The negative side is just because of the convention. The current is coming out instead of going in. And so that's the basic, it's a very simple theory. The thing is that although the theory looks easy, we don't have the luxury of vector calculation, right? It's just magnitudes, and this is a quick and easy method. So we don't have like state estimation. If you have the actual system model and you have a state estimation, then you have angles, and you are able to do vector determination. But we're just using magnitudes, and so some approximations have to be incorporated, and so the paper details these approximations and how we are able to determine the grid strength, so the Thevenin impedance, as measured by the Thevenin impedance. And we therefore different types of loads, a strong grid, a low strength, and a minimum acceptable grid. And also the method to be able to determine the change in voltage and change in current is to create some disturbances. We thought that two types of disturbances would be appropriate. Because these are at the disposal of the nuclear power operators. One of them would be just changing the transformer, some of the main transformer taps, just operating them, and that will create some variation in voltage and current, which we can use. Another thing is that you can switch in some of the loads, some motors, or some load, and also that will create a change or some perturbation that you can use to estimate the grid strengths. So what we did, just to show you the results, of course, because of the time limit. So we did that. There's good news is that in the loads that are dominant in a nuclear power station are constant power loads. So the motor dominant loads, which means that when you change something, when you change voltage conditions, the thing that tends to change is the reactive power. The active power tends to stay constant. And that's good for our purposes because Reactive power gives you, because the transmission line itself, or the Thevenin impedance, is dominantly reactive. So if the load change is also dominantly reactive, it acts along the same maximum sensitivity vector of change. The worst thing is that when you have Thevenin impedance reactive and then the load is active power, that's 90 degrees difference. The sensitivity along the voltage magnitude is going to be minimum. There will be change along the angle, but we're not measuring angles. We're only measuring magnitudes. So the good news is that for loads that are appropriate for power system, we get maximum visibility. This is the first. All right. Okay, I don't know what happened there, but let's go back. So the first table is showing loads, showing constant impedance model, which doesn't work very well. The second shows reactive model, reactive change, and you can see the green parts give us maximum resolution versus maximum accuracy. So where the green meets, when the estimation is good and the resolution is good, that's the two lower rows, then you get good visibility. Another type of disturbance was not tap changing, but switching in loads. Again, when we switch in loads, which are just active and reactive power, you don't get good results. There's not a lot of overlap, but I can see the last part is starting a motor. Start switching in a motor. When you switch in the motor that's dominantly reactive, you get very good resolution in terms of voltage magnitude, and you get very good accuracy as well. So that was the results that we got, and we've shown that the estimation is possible. We've shown that it's also good when you have dominantly reactive loads, which we do in nuclear power stations, and of course, if you have an online system, some nuclear power stations have it, some don't. If you have that, it makes it easier, but you can just switch in loads and observe the results. So this is going to be a very useful tool in terms of, or in the arsenal of nuclear power generations, and we think it's going to be useful. And with that, I think I've expired my time. So thank you very much indeed. Pleasure.
And so, the idea is the grid operator has to tell us if the grid's okay, but if he goes away, if the SCADA is lost, we wouldn't know that the grid's okay. So that's the idea behind the research. Can we determine the Thevenin impedance just from the normal load change that would be in the nuclear plant? It seems simple, but it's kind of like determining how small and what kind of load change.